A carbon-sulfur analyzer can produce a highly repeatable result and still report the wrong answer. If the portion tested does not represent the material, retains uncontrolled moisture, or fails to combust completely. That is why broad material compatibility must never be confused with a validated method. Steel, ores, cement, and non-ferrous alloys each require their own sampling, preparation, calibration, and verification controls. Steel and cast iron are often relatively homogeneous, but preparation still matters. Representative drilling or cutting must account for segregation, scale, oil, and graphite-rich regions. Chill samples may not reflect bulk material, while inconsistent chip size can affect combustion behavior. Calibration should cover the grade families in production, using matrix-matched certified reference materials. Borderline carbon or sulfur values warrant repeat testing because they may influence grade assignment, machinability, inclusion behavior, or melt correction. Non-ferrous alloys create a different challenge. Copper, nickel, aluminum, and other alloy families can vary in melting behavior, alloying additions, surface contamination, and combustion response. A general claim of non-ferrous capability is therefore insufficient. The laboratory must confirm complete combustion under the selected furnace program and demonstrate calibration performance for each relevant alloy family. Cleaning methods, sample geometry, accelerators, oxygen flow, and residue inspection all become part of that evidence. For ores, sampling uncertainty can dominate instrument uncertainty. Particle size, mineral distribution, gangue, and moisture may make a small test portion unrepresentative. Crushing, milling, drying, mixing, and subdivision must be controlled before analyzer performance can be judged. Replicate portions from one prepared lot help distinguish analytical variation from preparation and sampling variation. If those portions disagree widely, the first investigation should focus on homogeneity, not immediately on the detector. Cement and related powders introduce moisture, fines loss, and reporting basis risks. A stable weighed mass may not represent the intended dry material if moisture remains uncontrolled. Laboratories may need defined drying conditions, sealed storage, consistent powder transfer, and checks for lost fines. Reports must clearly state whether results are on an as-received or dried basis, with calibration and quality control samples treated consistently. The JIEBO CS996 high-frequency infrared carbon-sulfur analyzer is presented for steel, iron, alloys, non-ferrous metals, cement, and ores. Its stated standard sample weight is 0.5 grams, but that portion carries very different uncertainty as a metal chip, drilled sample, powder, or prepared mineral fraction. The product information describes carbon measurement from 0.0001% to 10.0000% and sulfur from 0.0001% to 3.5000%, along with low and high carbon analysis pools and an optional high sulfur pool. Buyers should establish which ranges, pools, furnace programs, and reference materials have been demonstrated on their actual matrices. Validation should be risk-based. Stable, homogeneous metals with established calibration may require clean preparation, blank checks, and routine reference verification. Variable alloys and unfamiliar grades need additional replicates, matrix match standards, and comparison with an existing method. Heterogeneous ores, moisture-sensitive powders, and samples with uncertain preparation histories demand defined sampling statistics, dry basis rules, preparation controls, replicate frequencies, and out-of-range procedures. Any new matrix should be treated as a controlled technical change. Test suitable references at low, middle, and high levels, define acceptance limits before testing, and retain an independent check sample. Reassess blank correction after changes to consumables, furnace conditions, or preparation. New accelerators, crucibles, mills, software, reporting bases, or critical suppliers should also trigger review. Reliable cross-matrix analysis ultimately depends on traceable method ownership. Reports should identify the material family, preparation basis, calibration version, reference material status, and validated range. Broad material coverage provides the starting point. Representative sampling, matrix-matched calibration, complete combustion, and documented replicate evidence turn it into a defensible result.